Okay, so let's get started. Today, more Metropolis Hastings. And when I say Metropolis Hastings, I really do mean this is MCMC. So Markov chain Monte Carlo algorithms or MCMC algorithms. MCMC algorithms, they're all this algorithm that we've been writing down. And I've written it down at least in a specific context. Let's see. A specific context over here. So I just want to back up to this example, and then we're going to move forward and start looking at some discrete Markov chains so that we can understand the theory behind this algorithm. So the best part of this algorithm to recognize is that it's 2 steps. At least in spirit, it's easy to implement. Okay, but there's a lot of things that can go wrong here. So going back to this example where I'm trying to learn mu from a normal example, and I'm writing down that I know sigma squared, so that we can just understand some technical details. I maybe would run this thing. Now we did talk about this right here, maybe being a normal distribution. So I have to pick something right here. And I think what we ended up doing is we picked normal mu, given mu t minus 1, and some tuning parameter. Okay, so I centered it where we were last time, and then I added some tunable variant for how much do I want to search and explore. I hope you can appreciate that in any problem that you go into and you really don't know the answer, you won't know how to tune that on the first go around. And so if the space that you're trying to explore is very diffused, you need to start sweeping through it faster. And if it's very, very narrow, then you need to move through slower so that you can learn everything and not always propose outside of things. And so I'll give you strategies for taking care of this in a couple lectures, but basically, in a nutshell, you run the thing, you see how well it works. If it's working poorly, you wiggle that around until you get something good. All MCMC algorithms differ by their proposal. Christina?
Regarding the step that you take, whether it's small or big, doesn't it depend on the variance of the data that we have?
You got it, the variance of the model. So if the model itself is very diffused, you need to sweep through it faster. So yeah, absolutely. So even like, it's not just even the model, but it's how much data you have. If you have a lot of data, then that thing gets geeky. And so all search problems are kind of theoretically impossible unless you know something about the model. So how do you know that what you have in search isn't the good stuff? If there's an infinite number of possibilities, you never quite know for sure. Of course, you can start coming into, I know an asymptotic property of this distribution. I know this distribution is maybe unimodal, something like that. So sometimes some mathematical inspection is necessary to know that you've converged to the right thing. But in complicated, multimodal spaces, you never know for sure. So you need to have diagnostics that you can follow and track after you look at the output of this algorithm. So what I'm writing down is theoretically true, it will converge to the right thing, but in practice, how do you check? So we have to go through all those issues. So it's not trivial how you come up with this. Saying that, I'm kind of pretending that the posterior that I'm trying to sample is likelihood times prior. My prior is flat. I could have written it in times 1 times 1. But since it's a flat prior, I'll just take it out of the equation. So I'm just writing down likelihood right here. And I'm pretending that I'm really not very knowledgeable about these likelihood functions. I'm pretending that I don't know that that's subnormal. So I'm not attempting to sample from it directly. Instead, I'm using some built-in functionality in my computer, some normal, locally centered proposal, and I'm doing this. And I'm saying eventually it'll sample from the right thing. Let's think about what would happen if I specified this a little bit differently. So here's just a quick question. Which proposal would be best? Is there even an answer to this question?
It depends.
I mean, the actual distribution.
Yeah. Thank you. So there is an answer. So let's imagine if I plugged in the true distribution pi mu and I happen to be using that as a proposal. And so,
But if you have the true distribution, you wouldn't be following this.
but let's just think about the algorithm. Take the algorithm to certain limits. So yeah, you would never do that. But let's just see what the algorithm does if you happen to be sampling from the right thing. If you do the right stuff, your algorithm shouldn't break, right? It should work even better. So answer, we should sample from pi mu, given x right here. So, and I'm going to be specific and say I know sigma squared of this. So what would happen, I would plug in that proposal right here. And so I'd plug in, instead of using this local proposal, I'd maybe use pi mu t minus 1 given x. And then I would use pi mu star given x. And that would be going in right here. So I would be using pi mu given x. Now, of course, to understand what I'm doing, you have to realize this is ridiculous. You wouldn't implement it, but we're just trying to understand how the algo performs. So what happens right here? If I plug this in, what is this ratio? It's 1. So it would be 1 in that case. Keep in mind, the numerator right here is just off from that thing in a proportionality constant because I haven't normalized this. And so I get samples with probability 1. So I'd just be doing all this extra calculation over the top. Propose a sample, I'm always going to take it. And so, okay, that's the right thing, that's good. So there is an answer to this question. It usually doesn't help you to do the optimal thing because we can never do the optimal thing. If we could do the optimal thing, we'd just go to the original problem, just do it directly. Okay, so the answers to these questions theoretically don't help us. Let me ask another question. Question: is a high acceptance rate a proxy for an efficient algorithm? So what I mean by efficient is how long do I need to run this thing before I converge to samples from the correct stationary target, what I'm trying to sample from, the posterior. What do you think? So I just showed this optimal prior that we might use, just be doing a bunch of flops for no reason and slowing down everything, but if I used it, I would be getting perfect samples every single time. I'm sampling from the right thing, and it didn't take me any burn-in to get there. My acceptance rate is always 1, and it's giving me samples from the true target. So that's good. Acceptance probability 1 seems really good. What do you think?
I'd say no, because you could get stuck still.
Could get stuck.
Right, so like if you are very likely to propose in one of the modes, then you'd only really be exploring that one.
So let's go back to a simpler example. You're injecting a bimodal example, and I get your point. That if you're bimodal and you got trapped somewhere, that you might always be sampling from that mode, but there's space over somewhere else. So that's a good example. Let's keep that in mind, and I'll tell you about bimodal sampling later. A localized proposal will not do bimodal sampling very well, because the stuff you want to jump to is very far away, presumably. The answer is still no. And so think about this. Think about a local proposal. So let's just write this down. This is a big deal. No. That's what makes this a little bit hard. So sometimes it is yes, and then sometimes it's no. But I like to just say in general, no. You can't just monitor that. Think about mu star being from a local proposal, which we know is not the right thing. It's just kind of wandering around in these circles. Mu t minus 1. And I'm going to say this variance, psi squared, is small, very small. Tiny. So I only tippy-toe. So I barely move. So think about what happens if I use this local proposal. What's the inverse proposal ratio? It's 1 because it's symmetric. Sometimes that's why we like that thing. So it comes out of the calculation. We don't even have to compute that part. And if psi squared was tiny, so what I'm talking about is something really, really peaky. right here. Probably even peakier than that. But let's say that I've got a mu t minus 1. Right here, this is my proposal variance. Psi, right here. And think about my true surface. Okay, maybe something like this. This might be my truth. Pi mu given x, sigma squared. Okay, so this thing is just going to be dancing around this space. So this is my proposal. This is G. And this right here is my target. So it's just wandering around. So let's say I had a point right here. This is where I was last time. And it's that high. Now let's say I propose something not very far away. Let's say it was right here. And then I come up and I compare it to its posterior target. They're very close to each other. And so this ratio right here is what I'm evaluating. My posterior target surface, it looks like that more diffuse surface. And so this thing's going to be very close to 1 because they're very close to each other on the same surface. And so this one actually is a little bit higher, so I'd go there. And so basically I can drive that proposal variance very small, and I'm always accepting. Seems like a good idea, but I've got this surface that I'm trying to explore, and I'm doing it super slowly, barely walking through that part of the space. I'll show you what the trace plots look like, but you can imagine they stick a lot. They barely move. You barely propose anything. And so that's kind of the unadventurous way of going through life. Always do exactly the same thing, and not a lot changes. And so again, this algorithm is like life. So every once in a while, you should go check something else out, is what it says. Otherwise, you're going to converge to your optimal solution in life very slowly. Okay, so still don't quite know how to do this. You know, how do we come up with the right proposal? And again, that's always the question. All we have is strategies. Okay, so let's think about the harder problem now. Move into trying to get the mean and the variance. So we're just going to switch gears real quickly. But before we do this, I want to show you a few equations that govern this algorithm, and I'm going to show you in a discrete sense how all this works. So this is where we left off in the conversation last time. So again, this algorithm is just a Markov chain, and we keep clicking through the Markov chain, which will possibly deliver us to some limiting distribution. So this is limiting to something. And so let's think about it in a discrete sense. What Markov chains do when they limit to something, if they do limit. And so consider a Markov chain. So discrete. And I'll just write it down like this. And so I'll write down a 3 by 3. So these are just transition probabilities. This is the transition. Of moving, let's do this one, so that my indices don't look exactly the same. Moving from state 2 to state 3. So that's what it's doing. So this is my transition thing. In this sense, this is a continuous analog. This is telling me how to transition, and there's some probability that I make the transition. How do I compute that probability? I multiply this by that. It's not a probability because this part is discrete. That's a probability, and this is a density. So the whole thing together are these two steps. One's continuous, one's discrete. So when I propose mu, that came from a continuous thing, and then I flipped a coin. Discrete. So I can't use density or probability to describe this, so I use the word rate. Okay, it's the mix of both these two steps. This is purely discrete. This is just flipping coins. So, but About the same sort of thing. Both Markov and both controlled by the same properties. So we stopped last time and we said what the Nstep transition looks like. So from last time, we showed the Nstep transition matrix is this. Raised to the nth power. Okay. So that's the Nstep transition. I just take this matrix, this is my one-step transition. If I want to see where I'd be in 2 steps and compute all those probabilities, I could either run through this Markov chain 2 times, see what it is. If I computed that whole thing on average, I'd end up getting a squared. So easy calculation, conditional probabilities. And so this is the Nstep transition. Let me show you an example of this, of what happens as n gets big. So that's the limiting distribution that we're getting. What does this limit to? And it might limit to a different answer every single time, or it might limit to the same answer every single time. And that's the difference between whether or not a limiting distribution exists or not. They don't always. So I've got some matrix. I made this. I didn't think about anything when I made it. I just really wanted to make sure I could get from anywhere to anywhere eventually. And there were no funny patterns. And I'll talk more about that. I'll show you examples with funny patterns and when you get trapped. But basically, I just developed this that I could get from anywhere to anywhere. I could have made all those zeros some other numbers if I wanted to, and it would have been obvious that I could get from anywhere to anywhere if I did that, because I could do it in one step. This requires a few more steps. So if I'm in state 3 right here, I automatically go to state 2. Where can I get from state 2? Anywhere. And so, and in state 1, it either puts me back in state 1 or to state 3, and then I can eventually maybe get to state 2 by going through state 3. So I can't get from state 1 to state 2 instantly, but I can eventually get from state 1 to state 2. So state 1 to state 3, state 3 brings me to state 2, and then I can get from anywhere to anywhere. So a quick inspection is you're not going to get trapped right here. Let's just think about this, a squared. Those are my 2-step transitions. So in 2 steps, I can get from anywhere to anywhere. And that's what I just kind of illustrated already. So that becomes dense. Let's think about in 3 steps, what happens. Those are those probabilities. Okay. And they all change depending on where I started from. So if I started in state 1, my probability of arriving everywhere is determined by that top row. If I started in state 2, the probability of moving to state 1 in 3 steps is different than if I started in state 1. So, and same thing with state 3. So all those numbers are different right there. Let's just see what happens on a 4th step. 5th step. 6th step. What I want you to see is these numbers are starting to look more and more similar. So while these numbers are different right here, the probability of arriving in state 1 when I started at state 1 is about 0.3. And the probability of arriving in state 1 after starting in state 2 or state 3 is about 0.3. They are different. We crank this up a whole bunch of times. So up to numerical precision, those are all the same numbers. So what this says is that the probability of being in state 1 is 0.2903 regardless of where I started from. That's a limiting distribution. So a limiting distribution is describing the probability of being in particular states, and if that settles down and converges to a probability irregardless of where you started from, then your stationary or your limiting distribution exists. Okay. So that's what a limiting distribution is. So limit n goes to infinity. If this ends up producing a set of numbers that is the same down all the columns, then you have a limiting distribution. Describes the limit if the columns converge. To the same numbers, and what it means when that happens is that these probabilities are the probabilities of being in those states irregardless of where we started from. So, same probabilities. Regardless of starting point. So when you start a Markov process or any process, you have to start from somewhere. So if it doesn't matter after a while and I can't detect where you started from, that's the limiting distribution. Okay, let me tell you about another type of distribution. Let's talk about this. So let's talk about a stationary distribution. So stationary distributions. So they're defined by this. So sum, and I'll just write it, probability of state J given state I times the probability of being in state I is going to be equal to the probability of being in state J. This is the prob, marginal prob. So this is the probability that doesn't consider how you got there. It's just the probability that you're there. So if you run through some process that isn't tracking you and can get you around the space, you can probably convince yourself that eventually there's just some probability of being in a particular state. If I have a random starting location, so this is a distribution concerning our starting value. So this is just thinking about how do I want to start this. I'm not going to choose, I'm going to flip a coin and decide where I'm going to start. And the question is there a way of flipping this coin such that the resulting probabilities of states that we get are governed by the same probability distribution? It turns out the answer is yes. This always has a solution. So the solution to this thing, where I'm looking for a function over pi, always exists. So let me just write down this as a fact. Fact, a solution to this always exists. Let me me write it just a little bit different. So instead of writing down these probabilities right here, I can write down this is Aij. Right here, these are the elements of my Markov chain. And all I'm doing is I'm summing over all the states I. I goes from 1 to the number of states. In my example that I wrote down, it's just 3. So that's what it is. And so this kind of looks like a typical sort of calculation that we figure out in statistics. This is just marginalization. So I have a conditional distribution. I'm upgrading it to a joint distribution. And then I'm just figuring out what pi is so that it is that marginal representation. So it's the marginal distribution from a joint. That's it. So all I'm doing in that equation is marginalizing out. So just like we do with all probability distribution functions, I do this sort of thing all the time. I've got a conditional distribution, f, a given b. I've got a marginal distribution, I'll call it mb. And I integrate over the space b, and I get the margin on a. We're used to doing those calculations. So marginalizing over a joint distribution. These are just the margins in the two different directions. So typical calculation. How would I write this in terms of linear algebra? I don't like writing this operator. So I want to write it just in terms of cap A.
Isn't that just matrix multiplication?
It is. Yeah, can you write it down?
So can I still call this?
You can call it, use cap A
Yeah.
in your notation.
So currently,
What's B? Okay, the margin. So that's pi I or something?
yeah.
Okay, so you write pi I.
That's it.
Okay, now do the whole calculation.
So
There's a whole system of these things, right?
yeah.
So really, all you're going to end up doing, if you keep those indices here, you're going to rewrite this equation, and you're just going to put an I there and a J there. So how do we do it as a system?
You mean you want to rewrite it?
I just want you to write this equation using cap A. Anybody want to help out Christina on this?
A pi equals pi.
A pi equals pi. So this is what Annie said. She said, why not do this?
Oh,
A pi equals pi. And where pi, I think Annie is saying this is pi 1 down to pi number of states. Is this what you said?
It may be transposed.
Yeah, right? So here's where everybody gets confused. Thank you, Christina, for kicking us off on that. I was really looking for this, but Christina was 2 seconds away from getting here. A lot of people jumped and they say, hey, let's write down a pi is equal to pi right here. Look at what's confusing right here, where our indices are. These get flipped around from right here. So the way we write matrix notation and conditional probability notation are transposes of each other. So this is actually equivalent to writing down A transpose equals to pi. So this is it. That's the same. They're equivalent to each other. So we want the solution in terms of pi. So our goal is to find the vector pi. In a continuous problem, this is harder. We've got an integration, and we have to solve through that integration for a continuous function. That's a hard calculation. In discrete land, this is a simple linear algebraic problem. How do you solve this? Does this problem look familiar to you?
Multiply
Yeah, it's
by
a
pi.
any value.
It's an eigenvector eigenvalue problem. That's right. So eigenvector, eigenvalue problems look like this. A V equals lambda V. Right, so that's what we normally do. I think this is pretty standard notation, where here's your eigenvalue, and here's the vector. And so, and matrices have solutions to these problems. This is taking it one step further. It's saying that there is an eigenvector associated with eigenvalue 1 in here. This right here says there's an eigenvector vector, which we've called pi, with eigenvalue 1. And that's kind of surprising because not all matrices have eigenpairs where there's an eigenvalue 1. It doesn't always happen. But for this sort of system, it's guaranteed. We're not going to go through the math to prove that, but what do you think it is? It's the distribution, so it's that constraint that makes everything sum up to 1 that does it. And so that constrained part of it forces there to be an eigenvalue of 1 in here. And in fact, that's the maximal eigenvalue in the whole system. And so if you go through a stochastics class that's heavy on linear algebra class, they'll have you prove all these things. And so that takes a little bit of work, and that's why I'm going to avoid it here. It turns out, here's an interesting fact, the second eigenvalue, the second biggest one, which is bounded by norm 1, because I'm saying that's the maximal one, we won't prove that, but I'll state it as a fact, ends up governing how fast you can move through the matrix. So how fast you can explore all the different steps. So that distance away from eigenvalue 1 is called the spectral gap. And it turns out a lot of theory-oriented MCMC people are trying to design algorithms with the spectral gap that says I can explore the space very, very fast. And that can be very difficult to prove explicitly and to come up with proofs like that. And so, but that's what a mathematician might be doing with these algorithms. And there's a whole bunch of people that do research just on that, showing what the eigensystem looks like in these big, complex, continuous processes with complex proposal systems. I can't usually prove. I can't usually calculate the spectral gap explicitly. So I have to come up with bounding theory to do that. Okay, so that's just a little bit of theory right here. And so we want to solve this problem. There is an infinite number of solutions to this problem, because I can multiply by any constant on any side, and it's still the same solution for pi. And so eigenvectors are not unique. I can multiply by constants, and it's still a vector in the same direction. And so our eigenvectors that we want do have a constraint on them. And so our constraint is just that these represent probabilities. So sum of the pi i's is equal to 1. You can write that a lot of different ways. Sometimes I might write that as pi transpose pi. Well, pi transposed times the 1 vector is equal to 1, is how you might do it, if you want to keep everything consistent. So I want to come up with a solution to this. And it's not hard to do. You might hear eigenvector, eigenvalue problem, and you realize computationally that's about the hardest problem you can try to solve with a matrix. If this is very big, that's a lot of calculation. But it turns out we don't need them all. We just need one of them, and I know which one I'm looking for. So that makes this problem much easier. So I can just rewrite all of this. So I'm going to rewrite everything. It's just, again, A transpose pi is equal to pi. And then I've got this constraint. I'm going to say my 1 vector, and I'm going to go the other way. I'm going to transpose that right here, and I'm going to multiply that by pi. And I'm going to say this thing is equal to 1. right over here. So that's the exact same system. 1 transpose times pi, pi transpose times 1. It's just a scalar either way. So I'm transposing a scalar. And I want it to equal to 1. So I'm multiplying by pi times that. And so this is a pretty easy problem to solve. I can end up doing this. A transpose minus the identity, 1 vector transpose is equal to 0. So this is a vector of zeros right here that was of length pi. And this is just a scalar. Times pi is equal. So this is just a solve. So now I just need to write down that pi is the solution to this. And it turns out pi is unique. So let's just do that on my computer real quick. See what the solution to this thing is. Yeah, so you're looking at the dimensions of all of this. And so this is an overdetermined system, but the constraint being equal to 1 ends up giving us the solution. So this right here, well, if we look at all of this, what does all of this look like? I think I've already encoded this a couple minutes before class. There it is. So that's all I want to do, and I want to, let's end up doing this. This, right here. So that's all that we're looking for, right here. And so, you might know what this thing is doing, right here, the backslash operator. You solve regression problems this way. So it ends up doing a QR sort of thing, and then does a solve. I wouldn't write inverse right here and invert this whole system. If you try to do it, this is what you're saying. It's in this case, it's 4 by 3. And you're not going to be able to come up with an inverse to that. And so this is what you're talking about, but the constraint actually helps us in all of this. So this is really just doing like a QR factorization sort of thing. When I solve it, I get those numbers. Let's go back to that. I clicked through it a few more times. And so my stationary distribution that I solved for, turns out it is the limiting distribution. Same probabilities of being in the states. So these numbers right there are those numbers. So that's how you solve for it. Of course, in a very big process, this is probably not the direction you would end up going. So you might use some numerical techniques or whatever, but it did do a lot of numerics for me in that way. So that's the connection between a stationary and a limiting distribution. So here's a fact. If the limiting distribution exists, it will be the stationary distribution. They are the same things. Sometimes limiting distributions do not exist for Markov chains. JD?
Can we quickly solve for pi by taking A transpose minus I inverse and then normalizing?
Maybe. Let me answer that afterwards. So I don't think so. I don't think it'll come out the same. You'll get maybe negative solutions in there. It's
Just to
wrong
point
with
out,
that.
A transpose minus I is not invertible, right? That's 1 is an eigenvalue for A transpose.
Yeah, let's go back to it and do our mental arithmetic later. I get confused in these things too. So, might be other ways to solve for this. The point being is that these are the same solutions. So let me write down a fact real quick. If a limiting distribution exists, it is stationary. So basically, if those columns end up converging to the same values, it'll be the solution to this other problem. There is a lot of beautiful linear algebra in here and hard proofs to work through, and they're fun, and I would encourage you all to go through it. So we're just going to bypass all of that. So let me show you a couple examples where a limiting distribution does not exist. Here's one. A is equal to the identity. I'll keep them 2 by 2s because it's sufficient to show. So what happens if I start in state 1, I stay in state 1. If I start in state 2, I stay in state 2 and I don't move. That's a Markov process right there. That is a well-defined Markov process. There are some undesirables about this Markov process is it doesn't bounce you around the space. Let me show you another one that does bounce you through the space. So you might be thinking, oh, okay, trapping is bad. But that's not the only bad thing that can happen. You can already power that up. I bet you can do that math in your head. So a to the n is going to be equal to the identity. So you don't just get trapped, just stay trapped. Here's another example. This is trapping. Consider this example. 0, 1, 1, 0. This is kind of flipping everything. So I do explore state 1 and state 2 all the time. It's determined which one I'm going to explore. It gets all through the space, but there's this really funny pattern right here. And if I power this thing up, I don't know what the matrix is. I'm not sure, because it keeps flipping everything around. And so I can't tell which state I'm going to be in. It depends on where I started from. So on even steps and odd steps, I'll either be in state 1 or state 2. And so if I'm in state 1 on an even step, so this one is on, if I started from state 1, right here, then I move to state 2 on the first step. And all odd steps will be in state 2. And so that's a little bit of a problem. And so it's unclear what the limit is right here because it's just going to flip which state you're in. And they're just flipping back and forth. So funny patterns, I'll say. So definitely determine which state you're going to be in dependent on the starting state. Let's think about stationary distributions for both of these. So is there a way that I can think about this limiting distribution, but I'm not explicitly iterating through everything? Well, it depends on how I start. If I make that stochastic, maybe there's a solution to this question. So A transpose pod equal to pod with this thing, 1 transpose pi is equal to 1. If I solve that, I'll come up with a solution. So pi in both of these examples, and I'll let you work it out real quick. What is it? Some mental math. Just try that one.
Any pi that sums to 1 will work for A, right?
Yeah, that's right, almost, right? So there's a lot of different ways to think about this. So what about for this example?
Yeah, to be the same 1/2, 1/2.
1/2, 1/2. Yeah, I kind of like it. 1/2. So if I flip a coin and make that stochastic my starting location, then I can find the answer to this. That's how a limiting distribution and a stationary distribution differ. So if I make the starting location random, then I can talk about this sort of what the distribution of the result is going to be. So turns out there's 3 conditions.
So what is it 1/2?
Just plug it in and you get a solution to the system. Solve that same thing, you get a 1/2. Okay. So there are 3 very intuitive conditions. For a limiting distribution to exist. So what it says, since I only have 3 minutes and I always go over, so I'm always ambitious in these last couple minutes, I'll be less ambitious. I'll just tell you about it real quick. So it says that where I'm starting from, I can get to anywhere with some positive probability in some number of steps. And so that's called irreducibility. So I can get from anywhere to anywhere. So I can move around. So, and I'm also going to say that, so let's just write this down. 1, can get anywhere. And there's a second condition that says I will come back to where I started from in a finite amount of time. Return in finite amount of time. These two conditions together tell me something. This says you will get back. So you will search everywhere with these two things. So if every place that I come from, I will return to in a finite amount of time, and I can get from anywhere to anywhere, it means eventually you will explore that space. So you can get anywhere. Together, this means you will get everywhere. But there's one more condition we need, and I need no funny patterns. I can't say that in multiples of 3 I get back, or in multiples of 4 I get back. In this problem, where we have this switching with the funny patterns, it was parity 2 that I get back. So every other thing I get back. And so I want to be able to say in multiples of 1, eventually I will get back. Okay. So I'm going to say this, no funny patterns, and 3, in multiples of 1, eventually we can return. Not in multiples of 2 or 3, so on and so forth. And so those are the 3 intuitive conditions. So it basically says I can get from anywhere to anywhere, get around the whole space, I will, and no funny patterns. That means that there is a limiting distribution. We won't prove that. So again, a whole math class on stochastic processes would walk you through all these proofs. So this is called irreducibility. Does anybody know what this one is called?
Positive recurrence.
Positive recurrence. So you will recur, and everybody will recur. So that's positive recurrence. Some people call these two together, ergodicity. That's some textbooks. I call all 3 of them together ergodicity. So you have to watch out for that word. So I'll write that down next time, and then we'll adapt this to our algorithm. So just here's the key crucial part. The algorithm is working through a limiting distribution. And we're saying that limit exists. So I'm going to guarantee in the algorithm that I wrote down, if it's properly written down, all those conditions will exist, and I'll get my stationary part in. And that's my goal. So let's come back next time and put all that together in the context of the algorithm. Thanks, you guys.